This is the Thursday, Friday lesson for the Unit 4, Week 4 Digital Interactive Notebook. You should be able to go in here and open up a copy that already has your name on it. Okay, let's start off with the glossary just as means of review. So numbers that are raised in the line of text that denote charge are superscript numbers. Subscript numbers are numbers lowered in the line of text that denote count. Electrons on the outermost orbital on the outside of an atom are valence electrons. Atoms are the most stable when they have full valence shells. Most atoms need 8 electrons to be full. Hydrogen only needs 2 electrons. That is the octet rule. The type of bonding that meets the octet rule by sharing electrons is covalent bonding. 2 electrons that are shared in between atoms is called a single bond. 2 electrons that are not part of a bond are a lone pair. So that's means of review. We'll do these other 4 as we go towards the end of this notebook. So last class we learned this new 8 steps way of drawing Lewis structures. So we're not pulling around individual electrons anymore, but we're kind of counting by 2s. We figured out how to add up the total number of valence electrons a molecule should have based on its atoms. You don't need to type anything in here. And so then here we also have a couple of the examples from last time. So this class we're going to double check some Lewis structures, namely carbon dioxide, methane, ammonia, and selenium difluoride. Then we're going to talk about Lewis structures in 3D shapes, which I've been leading up to for a couple classes here. And then last, we're going to finish up talking about molecule shape and polarity. So, the double checking of Lewis structures, we had to answer 2 questions. Does your drawing have the correct number of valence electrons? And do all the atoms in your drawing meet the octet rule? The answer to both questions should be yes. If the answer to both questions is not yes, then you likely have the wrong Lewis structure. There are a couple Lewis structures that are correct without meeting the octet rule, but we will make special note of those as we see them today. So the first one we're going to double check is carbon dioxide. So starting up here, the Lewis structure for carbon dioxide should have 16 total valence electrons because it has 1 carbon with blank valence electrons and 2 oxygens with blank valence electrons each. So 1 carbon has how many valence electrons? Well, let's slide over here. 1 carbon has 4 valence electrons. And you'll notice that this fill in the blank has a question mark in it right now. If we just type in 4, the question mark will still be there. So we have to go in and delete the question mark as we make our 4. So the Lewis structure for carbon dioxide should have 16 total valence electrons because it has 1 carbon with 4 valence electrons and 2 oxygens with blank valence electrons each. Each oxygen should have 6 valence electrons. So again, as I put in my 6, I need to make sure I delete that question mark first and then put in my 6. There we go. So if we have 2 6s is 12 and plus 4 gets us to 16. Okay, makes sense. The next step is we need to check the whole molecule and see if it has the right number of total valence electrons. So let's do that counting quick. So this Lewis structure has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Remember, we have to delete this question mark. 20 total valence electrons. It's supposed to have 16. This one has 20. That's not good. Let's check the other one on the other side. Okay, this molecule, this Lewis structure has 2, 4, 6, 8, 10, 12, 14, 16 valence electrons. That is the number that it's supposed to have. Okay, so now that we've checked the whole molecule, we need to check each atom. So let's do the one over here. So as we check each atom, we just check around each atom. This oxygen on the left here has 2, 4, 6, 8 valence electrons. The carbon in the center here has 2, 4, 6, 8 valence electrons. The oxygen on the right here has 2, 4, 6, 8 valence electrons. So does each atom meet the octet rule? This oxygen has 8 valence electrons, so yes, it meets the octet rule. This carbon has 8 valence electrons, so yes, it meets the octet rule. And this oxygen also meets the octet rule. Okay, let's look over here. This oxygen on the left has 2, 4, 6, 8 valence electrons. This carbon in the center has 2, 4, 6, 8 valence electrons. And this oxygen on the right has 2, 4, 6, 8 valence electrons. So this meets the octet rule, this meets the octet rule, and this meets the octet rule. So now, explain, is this a good Lewis structure for carbon dioxide and why? Well, this one on the left, this is not a good Lewis structure for CO2 because it has the wrong total number . This is not a good Lewis structure for carbon dioxide because it has the wrong number of total valence electrons. Because it has 20 total valence electrons, it's supposed to have 16. Yes, everything does meet the octet rule, but both the whole molecule and each atom have to be correct. So over here, is this a good Lewis structure for carbon dioxide? This is a good Lewis structure for CO2 because it has the correct total number of valence electrons and every atom meets the octet rule. Okay. So go through and do those same steps of counting, checking, and writing an explanation for CH4, carbon tetrahydride, also known as methane, NH3, nitrogen trihydride, or ammonia, and SEF2, which is just selenium difluoride. Pause the video and check these 3 Lewis structures now. Go ahead. Okay, that's our review of double-checking Lewis structures. Now we're going to move to Lewis structures and their 3D shapes. So, you're already familiar with 2D diagrams and 3D models. For example, we live on a 3-dimensional Earth that's out in space, but we often use 2D diagrams or 2-dimensional maps to show locations and places because they're just easier to draw and it's easier to make something 2D by drawing than to build something 3D by building a model. The same has been true with covalent molecules so far. These drawings are all 2-dimensional diagrams. In the real world, these molecules are in 3D. So we're going to be exploring 3D models of the 3D shapes that these 2-dimensional drawings make. And to help with that, we're going to use a PhET 3D model simulator. So we'll click here to open the simulator. And then it gives you this little molecule shapes link down here. and I want to click on real molecules. Okay. So it says make sure that you check these 3 checkboxes before you start. And what I'm going to want to do is I'm going to want to have 2 windows open next to each other. So I will get out of that. Hey, I know that guy. And I will drag this molecule shapes thing over here, and we'll go like that. So we do want to check these boxes that say molecule geometry and electron geometry. We also can, though you don't have to, go click here, go to options, show outer lone pairs, and then we can look through several different molecules like that. If it makes it simpler to look at, we can turn off this show outer lone pairs, and it will not show the lone pairs on the outside atoms. But for now, because it's more accurate, I want to leave that on. Okay, and we've got these 6 arrows here. It says use this simulator to fill out the table on the next page. And there's these 5. So we're starting with CH4. So here I'm going to select CH4, and I can grab the molecule and spin it around if I so choose. This is what a 3-dimensional CH4 looks like. So how many other atoms are bonded to the center atom? Well, our center atom is carbon, and we have 1, 2, 3, 4 hydrogens, so the answer is 4. How many lone pairs are on the center atom? Well, I don't see any lone pairs in either the model or the Lewis structure on the center atom, so I will say 0. What does our 3D model look like? Well, it looks like, this one. So I'll drag that one in to show that as our 3D model. Now it's asking for the name of both the molecular geometry and the electron geometry. So if we look down here, we can see that the molecule name is tetrahedral. You can see that the molecule name is tetrahedral. We might have to make that font a little smaller to get it to fit. And the electron geometry is also tetrahedral. And again, if it doesn't fit, make the font a little smaller. There we go. So now I'll go over to do NH3, which is our next one. How many other atoms are bonded to the center atom? Well, here we've got nitrogen is the center atom, and we've got 1, 2, 3 hydrogens bonded, so we'll say 3. How many lone pairs are on the center atom? Well, it looks like we have 1 lone pair. And it looks like this one. So what is the name of this molecular geometry? Well, it is trigonal pyramidal, because if you look at the 3D shape, it's kind of like a pyramid. If you don't look at the valence electrons, the base here is kind of like a pyramid, where this blue center nitrogen is the top of our period, and then these are the base. And it's trigonal pyramidal because it's a 3-sided pyramid with 3 points at the base instead of 4 points at the base. Because it's trigonal pyramidal because it has 3 points at the base, as opposed to other pyramids that have 4 points at the base. Okay, so now pause the video and you can do H2O CO2, and BF3. Careful with CO2 and BF3 because when it asks you to count how many lone pairs are on the center atom, we're counting the lone pairs that are on the center atom, not the lone pairs on the oxygens or on the fluorides, just the lone pairs on the center atom. Pause the video now and complete your table. Okay, let's get back to it. So why do these different 3D shapes happen? Well, just as opposites, what do opposites do to each other? Remember, I married somebody who is smart and attractive, so we know that opposites attract. That also means that similar charges will repel or push each other away. VSEPR stands for valence, shell, electron, pair, repulsion. Where we know that valence electrons are the electrons involved in bonding. The shell is trying to be the full shell that has the 8 electrons. Electrons are electrons. We know electrons come in pairs, either lone pairs or single bonds. And then repulsion, similar charges will repel each other. So all the parts attached to an atom will spread out as far away from each other as possible, including bonded atoms and lone pairs. So in a 3D space, if these 4 atoms at the edge of this purple atom are trying to get as far away from each other as possible, they're not going to spread out flat. They'll have more room to be even farther away from each other if they spread and twist into 3D to get even further. The same is true even if it's not atoms that are on the center atom, that are bonded to the center atom, but lone pairs will also spread and twist away to create these different shapes. And here we've got a great video with this guy who films himself drawing and using 3D models to explain it. So check out that video if you're interested. So now here we're going to get into the 3D model and explain some of that. So formula, CH4, Lewis structure, we've got the C, we've got our 4 H's. How many other atoms are bonded to the center atom? Well, there were 4. How many lone pairs are on the center atom? There are 0 lone pairs. Here's the 3D model. Why does the 3D shape look like this? The 4 gray atoms want to be as far away from each other as possible. There are 0 lone pairs on the center atom to push them together. So, all right, that fits with what we know about VSEPR theory. What about when instead of having 4 atoms bonded to the center, there are 3, and instead of 0 lone pairs, we have 1. Why does the shape look like this in the 3D model? What do we know is there but isn't shown in this 3D model picture? Well, in this case, okay, so we know from the Lewis structure, we know from the Lewis structure that there should be a lone pair on here, and in the models it doesn't always show the lone pair. But because we know it's there, we know that these 3 atoms on the center atom aren't going to spread out totally flat like they would to get the most space from each other, but they're going to be pushed down slightly by a lone pair that we can't see because electrons are much, much smaller than any atoms that we'd have. Okay, pause the video now and complete the rest of this 3D explanation slide. Thank you for pausing. Okay, we have done 2 of the 3 things we were going to do for this notebook. So let's now talk about molecule shape and polarity. We'll start with partial charges. So atoms in a molecule with lone pairs are going to have a partially what charge? Well, we know the electrons are negative, and this is a negative sign, so it'll be a partially negative charge. Atoms in a molecule without lone pairs have a partially positive charge, especially hydrogen. So now it says to label the atoms of these molecules as partially positive or partially negative. This nitrogen has a lone pair, so we're going to label that as partially negative. This hydrogen does not have a lone pair, so we'll mark that as partially positive. This hydrogen doesn't have a lone pair, so we'll mark that as partially positive. This hydrogen doesn't have a lone pair, so we'll mark that as partially positive. This CH4 is a little strange because it looks like because there's no lone pairs that this would all be partially positive. But if we only have partially positives, there'll be no partially negative to balance it out. So because of differences in electronegativity, if the only other thing is a hydrogen, hydrogen's generally always going to give the partially positive charge in here, which would make this carbon, as unlikely as it seems, partially negative. How about that? Okay, so pause the video now and do these other 2 on your own. Go ahead. Thank you for pausing. Okay, now we're going to talk about polarity and what that has to do with these partial charges. So magnets are polar because they've got this positive side and negative side, and molecules are also polar. And I like this YouTube video, shows a good trick that works for smaller molecules where there's just one center atom. This trick unfortunately doesn't work for larger molecules, but it's good for where we're at starting off. So if a central atom has different atoms or lone pairs attached to it, then that atom will have a positive side and a negative side. And that atom will be polar. So this atom, this molecule, it has this central carbon, and then we've got hydrogen, hydrogen, hydrogen. Those are all the same, but then we've got a chlorine over here. That's different. So because there's different stuff attached to the center atom, then it will be polar. If everything coming off the central atom is the same, then that atom will not have a positive side and a negative side. That atom will be nonpolar. Okay, so go through here and explain why these molecules are polar or nonpolar. So H2O is a polar molecule because, well, what did we say back here? Oh, it has lone pairs attached to the center atom. Because it has lone pairs attached to the center atom, there we go. All right, do the same thing for these other 5. And then over here, it just gives you the formula, and you need to build it and then determine if it is polar or nonpolar and explain why. This last one down here, you'll notice it doesn't have a center atom, and it doesn't really follow the rule we learned back here. I will tell you that this is a nonpolar molecule, and see if you can explain why. All right, that's it for this week. Remember to turn this in when you're done, and we will see you next week when we only have 2 more weeks left of classes in 2020. Woo! Bye.